Hi, everyone. Welcome. My name is Kathy Hill, and I'm WITI's webinar manager, and we're so thrilled to have you with us today. We have a great hour planned. We have two great presenters with us today. We have Kevin Walsh. Hi, Kevin.
Hello.
And we have David Pelkey. Hi, Kevin. Or sorry. Hi, David. Hi. I'm getting confused. Hi, David. Welcome.
Hello.
And they're going to be talking about 5G. And before we get started, I just want to go over a couple quick reminders. I am recording today's session as always. If you'd like to come back and listen to the recording and see their slides, you can do so at the link that I've put in the chat box. And the chat box is also where they're going to be taking your questions and comments from. So please go ahead and type them in there. I do want to mention that there is a little icon above our heads for Q&A. And if you would, don't use that. Go ahead and use the chat box. It makes it a lot easier for us to access your questions. And everyone else can see the question too, which is great because I can guarantee if you have a question, someone else is thinking the same thing. So without further ado, let me go ahead and introduce our presenters and we will get started. Kevin Walsh is Vice President of Mobile Marketing for Skyworks Solutions, and he's responsible for supporting mobile operator engagements as well as developing Skyworks' product roadmap and go-to-market strategy for the emerging 5G ecosystem. And David Pelkey is a Senior Technical Director of Systems Engineering at Skyworks Solutions, and he's responsible for providing technical direction on product development and partnerships and advising on next-generation communication standards such as 5G. So I'm going to go ahead and turn the webinar over to Kevin. And Kevin, go ahead and take it away.
Oh, Kathy, thank you very much. So, first of all, I'd like to thank everyone for joining in. Really, what we want to do is talk about a subject that, of course, has taken a lot of the air in the room. So, everyone's talking about 5G. A little history: Dave and I have been involved in 5G development at Skyworks for the last 3 years or so. And what we want to do is just kind of give you a little bit of a taste of, the journey that we took, how we got here, some of the decisions that we made, and what that means both from a device perspective and then into the front end, which is our specialty here at Skyworks. So come on the journey with us, and hopefully you'll be the wiser at the end of it. One of the things that really, from a consumer or user aspect is really how do we deal with our devices? Our devices really are the lifeline. You go to any mall or airport, everyone's consuming data on their phones, and it's really become ubiquitous. From any age group that you can see, and it's really we have the advantage of traveling globally, and it's not just a U.S. phenomenon. It's really taken off globally. And what we're trying to do, and the industry's trying to do with 5G, is really make that experience and get it better for the consumers. And probably what's most identifiable for folks is, you put on a video or a YouTube, you want that instant experience, and really that is a combination of the network and the device. So from a radio perspective, what we're trying to do, especially as we move to 5G, is really get that experience better. We take a look at devices, on the network, and it's really about data rates and speeds. And we're going to talk about the techniques that we use to try to make improvements to the condition across the board. The data rates, if you looked at them, are really a phenomenon of how we use the radio spectrum. And really the telltale sign is, latency in the network. So when we get good signals and they're transferred fast, we get a great user experience. Where people start to struggle is if we start to get the buffering wheel, you can tell that your frustration level goes up. So really we'll bring the practical aspects of how we get that done to give you a better positive experience on the network. like I said, we've been involved in the 5G development for the last couple of years, but really there's a cadence in the market where we're seeing a transition in the cellular generation about once every decade. So you can go back from 2G to 3G to 4G. Those were all developments that were really meant to bring us going from the voice environment of 2G into starting data in 3G and really the LTE era in 4G. And now we're making the transition of 5G. And 5G is going to be very different from the the 3G to 4G transition. It's really going to open up the market. I think the spaces are going to be quite different. The applications are going to be quite different. You're going to have fiber-like experience on your devices anywhere in the world and at any mobility rate. So that's really a challenge for the industry. So we're really going to raise the bar in terms of performance, but we want to be able to give like gigabit type experience to the device anytime, anywhere. And so those are the IMT 2020 requirements that were put out, and I can say we're well on the path to making sure that we can deliver that to the marketplace. As I said, 5G is different in that it's opening up many different market segments. If you look before, it was really about getting better performance at a cell phone. So the cell phone converted from voice to data and really talked about getting better cell phone. Now we're starting to see people are realizing if you have mobile data and it's good enough bandwidth and it's fast enough, you can enable new industries. And that's really, we're on the cusp of a very disruptive time. We're going to start seeing things on machine learning, VR, AR. Maybe you can do, telemedicine. Maybe you can do autonomous vehicles, industrial IoT. All these are going to be new applications enabled by 5G, and they'll take different compartments of 5G. Some may be at millimeter wave, some may be at sub a gigahertz, could be in 3.5 gigahertz. It's just going to take all the spectrum and tools available to make sure we can enable different end use applications. I wanted to talk a little bit about the 5G adoption and really about what we consider 5G. It really started in release 15. So 3GPP is the industry standards group that really embodies the cellular requirements. So we participate on that. And this is really the start of the 5G era with the release 15. We are now finished with release 15, working on release 16, which will be an extension of release 15. And then we'll go into release 17 and 18. And all that means is every time we do a release, there's more features, more ability for the networks to employ different radio protocols. So we as an industry will agree what standards and features will be embodied. That gets encased in a release, and then that moves into deployment through the networks and into the devices. You can see that since about mid of 2018, there's been a lot of 5G trials. You'll probably have heard a lot of things in the news in terms of 5G capable, 5G enabled radios. It's really very early days from a 5G perspective. The networks are really on trial networks. It's not rolled out all the way. But we do see a phase of commercialization kind of from 2019 to 2021, 22. That's when you're really going to start to see much more rollout of commercially available networks and devices. You'll see a lot of advertisement. You'll hear a lot of carriers argue against each other, T-Mobile and AT&T and things like that. But it's really in the industry's best foot forward that we're going to move forward, get those devices out to market. So Then we see a mass commercialization phase, and that's more in the 2022 to 2025 era. And then we'll start to see standalone networks and things like that. And we'll get into a little bit more details on that. But you can see that the pre-planning stage to get 5G out, is probably on the order of five years, and we've already been 3 years into it. So we really see we're right on the cusp of commercialization for 5G systems. I wanted to talk a little bit about the ecosystem, and you really have to have a lot of the pieces of the puzzle come together at the same time to be successful in terms of 5G launches. So, from a Skyworks perspective, we're involved. We're involved at the standardization at 5G. And 3GPP, and we work a lot with platform vendors. So you'll hear announcements from Qualcomm, Intel, MediaTek, Samsung, HiSilicon. So those are the folks that are doing the baseband and transceiver portion of the segment as well. You'll hear a lot, especially as we go into February. That's the time that Mobile World Congress is convening in Barcelona. There'll be a lot of announcements about types of devices, and those can come from, Samsung, Google, Lenovo, Oppo, Vivo, OnePlus. You'll just see a myriad of announcements in that time frame. So this portion of the ecosystem is really working hand in hand with the operators. So it's the AT&Ts, Verizon, T-Mobile, China Mobile, Vodafone. All the global operators have put out their specifications, and both the front-end providers, the platform providers, and the OEMs are working to deliver standard compliant material to those devices. And we can't forget about infrastructure. Infrastructure precedes the rollout of networks. So we have to have the infrastructure on the network and then the devices to support that. So we work closely with our infrastructure providers as well. So names that you would know: Ericsson, Nokia, Huawei, in that realm. I think from a global perspective, what I see a lot of is there is an element of national pride, if you will. So certainly there's 5G initiatives in every continent and every country in the world. And every region has its own unique market that kind of dictates the solutions. In the US, there's very little TDD in the cellular bands, so you start to see a movement towards millimeter wave devices in the U.S. So certainly some sub-6 gigahertz activity, but and LTE refarming, but definitely a bent towards millimeter wave type devices. China's been very aggressive in 5G rollouts, has done trials, and we see that they'll be commercially available in the 2020 timeframe. South Korea is a very advanced telecom country. Of course, they have Samsung and LG there, so they really try to get out ahead of any technology curve, as well as Japan. So they'll be definitely having both trial and commercial networks in the second half of 19 and going into 2020. European Union, it really just depends on the operators. There's some that are more aggressive to roll that out, and they'll be coming to market with 5G devices probably in 2020 as well. The other aspect, we see that a lot of the operators, they spend a lot of money on spectrum. You've seen spectrum auctions and seen very large monetary assessments to those. They spend billions and billions of dollars for spectrum, and that's really from our perspective, that's all opportunity where if people are investing in spectrum, they're going to want to monetize that. So that really directs what we do. So from our perspective, whether it's below gigahertz, low frequencies, maybe FDD in narrow channels, it could be in the 3 to 6 gigahertz range. That's a new band opening up that has wider channel bandwidth. So you can start to see, you're starting to get bigger chunks of available bandwidth. And newly, you're starting to see TDD bands in millimeter wave, whether it's 28 or 40, or even you'll start to see that higher. If the operators have spent and invested money, they're going to want to be able to make that a use case for 5G. And from the get-go of 5G, we're seeing devices in all frequency bands, whether it's LTE refarming, for existing spectrum, whether it's new TDD opportunities in the sub-6 gigahertz range that we talk about, or it's millimeter wave activity. It's definitely areas that you'll see in devices. And it could be a device, could be a smartphone, could be a customer premises equipment. It can come in all sorts of forms. The characteristics of the RF spectrum are such that the low frequency waves really, they just travel longer. So you get much broader coverage, but you have narrow channels, so you can't get the capacity. Whereas at the other end, if you have, very high millimeter wave frequency, you can get a lot of bandwidth, so you get a lot of capacity, but the radio waves don't travel as far. So all that has to be taken into account. So the different user business case will really dictate, what frequency we're trying to do and at what cost point and performance point we're trying to achieve. But the takeaway from this is, if there's spectrum and the operators have it, they'll figure out a way to monetize that. I wanted to just walk through a little bit of how we're going to move from the LTE world that we're in now to the 5G world. So I'll do kind of a simplistic view. Dave will give you a much more technical view later on of how we do that. But really, we're in a LTE Advanced Pro world. So that means we're at release 13 and 14 in the networks, and we're going into the 5G era. So really what you're seeing, and you even see that played out with some of the operators in terms of their messaging. They'll call 5GE, which is really LTE Advanced Pro network moving towards a 5G network. So people want to get onto the 5G bandwagon as early as possible. We'll show you some of the techniques that we do to get there, and then dive into more of the technical aspects in a little bit. So one way that we can get more data is to change the modulation. So it's really the number of bits per symbol we can get. And we like to kind of say, hey, that's the speed of the cars on the highway. If we're really fast in the fast lane, that's a higher QAM application. The other thing we can do is start to add carrier aggregation. And carrier aggregation means we're adding bandwidth or extra channels. We're basically stitching together channels of bandwidth to get more data. So we're really trying to open the pipe, if you will. And really, from a conceptual, we're trying to add more lanes. So we can speed up the cars with modulation. And if we add more lanes, that's wider bandwidth. So those are two techniques that we're using right now: carrier aggregation and modulation, even in the 4G networks. If we're trying to, if we add more multipath devices, that's adding new roads. That's our MIMO capability. So instead of streaming data on one path, we could actually make that into 2 paths in the uplink or 4 paths in the downlink. And that's really just adding more capacity, more bandwidth. So that's really showing up and being field proven now on networks. So a lot of the phones that you have today are employing all the techniques that we just talked about. They support 2 or 3 downlink carrier aggregation, higher order QAM than what they used to, and they're also supporting multi-user MIMO on the receive side. And finally, while it's not commercially available, it certainly exists in the lab. We're starting to see a lot of activity in millimeter wave. And the analogy for millimeter waves is we're just adding a new transport mechanism. So we've got our highways full up. Now we're going to add an ability to go from city to city by adding an airport, and it's a totally different ball game, and it really does deliver quite a different experience for anybody that's been on the road for 8 hours versus taking a plane. I think you can appreciate that analogy. So that's really one of the aspects that we see. So we see all of these coming into play in 5G, as well as some other techniques that we'll talk about in the next thing. So in terms of 5G, in the release 15, what we saw was really an exploration and expansion of MIMO. So we're starting to see for the first time, while it was available on LTE networks, it's mandatory in the 5G networks. So we're starting to see 4x4 downlink MIMO techniques. A lot of the operators want to see 2x2 uplink MIMO as well. We see a lot of cases for dual connectivity, and that's really saying that there's an existing network for 4G, and we're going to start to layer 5G capabilities on top of it. So anytime there's a transition in networks, we want to be able to reuse what's already existing, what they've spent money for, and then add in the 5G features piece by piece till they build out the whole network. So we'll support dual connectivity in the device. I talked about new bands. So one of the biggest areas of new bands is in the mid-band spectrum. So below 6 or 7 gigahertz, we start to see a lot of TDD wide bandwidth available. That's really going to be disruptive from a user experience. Right now, you may see 60 megahertz on your devices. You're going to add another 120 megahertz on top of that for 5G, which is going to be a strong benefit as well as potential millimeter wave devices. And all that combines to much higher bandwidth, much higher data rates, and we'll get into the details there in a second. As I say, we're very involved in standardization, and what we see is, there's going to be, anytime there's a disruption, there's some uncertainty as to what's going to be required. You talk to an operator 6 months ago, the story will change. 3 months later, it'll change to last week. So what we try to do is figure out. Our job is to try to figure out what's going to be required. So we try to synthesize the information across the globe, across operators, through all of the both chipset platform companies and through the device manufacturers, and really try to take that. So we think that 4x4 downlink MIMO is a requirement from techniques such as SRS hopping. It's a technique to improve the downlink signal, and will be required. 2x2 uplink MIMO. It's going to be probably by price tier. High power is going to definitely be required, and then there's some other techniques here, whether it's APT or ET. We try to forecast that by chipset. Which all that's to say is, from a solution provider for the RF front end, we have to take into account a lot of different frequencies, a lot of different features, and make sure we can deliver that in time for the market. So now at this point, I'm going to bring in Dave Pelkey. He's our senior systems engineer. He's going to talk a little bit about the the differences and how we build that signal up and the capacity, and then finally what that means for the RF front end. Go
Thanks, Kevin.
ahead, Dave.
So to break down some of these aspects in terms of, how do they make a difference in terms of how we see data rates in our handsets. What we see up the top here is Shannon's limit base capacity formula. It's an expression for the bits per second. It's an upper limit on the ability or the maximum data rate that might be transmitted through a certain bandwidth channel in the presence of noise. And what we see is there's a number of factors, and they're all mathematically combined to produce this data rate. The first of which is this N, which expresses the MIMO order. So as Kevin mentioned, multiple in, multiple out is a technique by which we transmit different signals from different antennas, a number N antennas, and then those are received as well by that same number of antennas at the receiver. And of course, each antenna is going to receive on that same frequency channel an overlapped version of everything that's being transmitted from all the antennas. But because the antennas are orthogonal and different, and we get a lot of reflections, and the radio environments are different for each of the signals as they make their way to the receiving antennas, we can, in the end, separate those out. And this MIMO technique has been a fundamental basis for LTE, and now for 5G, it'll be even extended beyond. And this linear multiplier means that we can basically take this very expensive spectrum of the operator and double or quadruple the amount of data that we're able to get through in a given amount of time. So it's really important. The bandwidth, this BW term, comes next, and as Kevin mentioned, that's critically important as well as a linear multiplier. And as we extend channel sizes with 5G, we continue this exponential growth in carrier aggregation, where we take multiple carriers and combine them for even larger bandwidths. And so these linear multipliers combine together to produce huge increases in data rate. And what you see in the last term is a logarithm around the signal to noise ratio. And that's a thing that really allows us or enables for a certain order of modulation. So as we digitally modulate a signal and transmit it through the air, that it's composed of a certain number of bits per symbol. And this QAM, or this modulation index, allows us to send more bits per second, effectively assigning more bits per symbol. But you can see here that it's a function of a logarithmic contribution to the bits per second. So we get huge improvements in our overall data rate, but it eventually mitigates. Eventually you need so much signal to noise ratio to get to the better higher order modulations that eventually you have less and less incremental relative percentage impact. So as we look at 4G, includes all of these aspects, but 5G is going to extend those significantly. And this next slide really talks about one of the most important of those, of course, is the bandwidth. So we currently have been over the last decade on an exponential growth curve in terms of the number of combinations of different bands and the ability to combine different channels in different bands or different channels in the same band in LTE in order to take what's a maximum 20 megahertz channel bandwidth and try to extend that single component carrier to try to get 2 CCs or 2 component carriers and double the bandwidth there. And we keep adding, multiple carriers and basically turning on multiple RF paths in the radio simultaneously to try to get the bandwidth extended. And you can see here that the number of component carriers has been defined progressively increasing. We're well over 1,000 CA combinations now. The complexity in the phone as we turn on all of these simultaneous RF receive paths is really gotten quite large. And if you look on the right, we can see that the incremental impact of adding these component carriers really has this strong linear multiplication. And of course, 5G now starts to combine not just 20 megahertz carriers, but up to 100 megahertz component carriers. So the bandwidth effect is even that much more significant. So this next slide, there's a lot of math, but just in the interest of completeness, it kind of breaks down how these factors contribute to the very specific data rates that we might expect. And then we'll talk a little bit about what that means in terms of the use of the phone. So we start with the MIMO order, and in the case of, say, a 4x4 downlink MIMO connection, we might have a linear multiplier, a factor of 4, over a single SISO condition. The modulation index here expressed 256 QAM, which is basically 8 bits per symbol. And then we've done this case example, takes 3 20 megahertz channels for a total of 60 megahertz. And we're quantifying that as these 3 20 megahertz channels. It's a frequency division duplex or constant 100% duty cycle transmission or reception. And then we break down all the details in terms of how these translate for a 20 megahertz channel in terms of how many symbols per second are going to get through the pipe. And at the end, when we multiply all this together, we get this tremendously large 1.2 gigabit per second number. And so LTE Advanced Pro, as Kevin indicated, is able to deliver gigabit per second data rates today. So 5G just starts with this number and takes it up from there. But we normally don't experience that actual peak data rate. So you potentially could if all those conditions combine and you've got the right MIMO order and modulation index and full bandwidth and so on. But oftentimes we don't. And I'm going to go into a little bit of detail in terms of how these features are actually experienced in the cell, in the network, when you're actually using your phone. So this little hemisphere plot indicates by color some of these different aspects. We've got modulation order on the left, and we have the aggregated bandwidth in blue in the center, and we got MIMO order on the right in green. And what you can see is that the center here, meant to express close proximity to the tower, which would be right at the center there, we're able to get very high, say, modulation order. We've got very good signal to noise. We've got a direct line of sight, and we're quite close to the tower. And the radio conditions are really excellent. But as we travel in distance further from the tower, what we find is that our signal to noise will start to fall off. And these challenges that Kevin talked about, where the signal propagation results in loss and there's obscurity as you go into a building. We use our phones 75% of the time indoors. These kind of effects will reduce the signal amplitude that's received on your smartphone antenna. And eventually it gets tougher and tougher to actually receive the higher order modulations, and you have to back off to QPSK, which is only 2 bits per symbol as you get closer to cell edge. Similarly, in reception, you've got MIMO order, and so you start close to the tower, and hopefully in a multipath rich environment with a lot of reflections and good orthogonality and great signal to noise ratio, and you're able to support 4x4 downlink MIMO and get that 4 times multiplier for your data rate in reception. But eventually your SNR may decrease, and you may have to back off to a 2x2 MIMO and so on. And eventually when you get to cell edge, the use of multiple antennas can be changed somewhat from trying to send different data streams or data layers overlapping on that channel to sending the same data stream and receiving it amongst all your antennas and basically doing cross correlation to try to extract that single data stream, but you've got a different view of it. It's like a second look, and you can actually improve your SNR by about a factor of 2 in order to receive better at cell edge. So you get less bits through the pipe, but using this technique, you're able to improve the cell edge reception quite a bit. And so you can see from these two linear multipliers on the data rate that they actually start quite strong in the center, where hopefully you're achieving something closer to peak data rates. But then quite quickly throughout the cell, you fall off to a much lower average and eventually to cell edge performance. And really it's the cell edge performance that we most experience when we're in good conditions. We oftentimes don't notice. Our phone responds instantaneously and we enjoy the service. We only really notice when it starts to become more of a struggle with that buffering wheel. The aspects in the center have to do with bandwidth. And what we see here is that all the way from partial allocations to single component carriers, and as we kind of extend the bandwidth with combinations of LTE 20 megahertz channels, say as an example, that we can extend the bandwidth and significantly increase the data rate. And because in the downlink, when the tower is transmitting to the receiver on the handset, the transmit power is typically fixed. And so you can basically transmit extended bandwidths, capacity limited, of course, to any one user, depending. And so you could be at cell edge and still receive a significant portion of the bandwidth at reasonable SNR. So these are some of the factors that have to do in terms of the geography throughout the cell, as we're trying to optimize and maximize the downlink data rate. And of course, that's really what we're all using our phones for. Most of the time we're downloading videos and browsing the web, and most of the data is on the downlink as we receive it on our smartphones. But in addition, we have, of course, Uplink. And so when it comes time to transmit data from the smartphone, we have a different set of challenges, some of which are similar to the downlink. We see that, as we're close to the tower, we're going to have very good SNR, and we can typically transmit at very high modulation order, a lot of bits per symbol, and very fast bit transmission through the pipe. And we're also able to have certain transmission modes. In certain cases, certain hardware will support 2x2 uplink MIMO, so that you can actually double the data rate in uplink, depending on how your architecture and your hardware are configured. But what you see here in terms of the bandwidth is an interesting limitation in terms of the uplink, and we'll get into a little more detail in terms of how that impacts the overall coverage throughout the network. That if we transmit on a 20 megahertz channel, our modulation in LTE and even towards 5G, they're made up of smaller portions of frequency called resource blocks. And these are split up into small 180 kilohertz sections. And typically in a 20 megahertz channel, you're going to have 100 so-called resource blocks, or RBs. And there's a fundamental asymmetry in terms of the uplink and the downlink in the cell. The transmitter at the base station is quite high power, 40 watts, and there may be 4 antennas in a certain sector of the cell. But coming from the smartphone, you only have typically a quarter watt. There's limitations on how much radiated power we're able to transmit based on regulatory limits, and there's also a lot of consideration for the current consumption and the total power available from the mobile battery. So if we're trying to transmit the entire modulation, the entire 100 RBs, and say we transmit a total 23 dBm for that channel, then each of these RBs, 100 of them, each one would have 3 dBm, and so that small amount of power per RB becomes quite a limitation when the signal is trying to be received at the base station. You get to cell edge, and you may not have enough SNR to maintain the link, and so the network will typically change the amount of the number of RBs that you're transmitting in an effort to try to improve or increase the total power per RB. So we go from 100 RBs, we get down to 1 RB, and now that 1 RB has 23 dBm instead of just 3, and we've increased its power by a factor of 100, and so we're able to significantly extend the link. The asymmetry I talked about is because on the receive side, both on the handset and the receiver in the base station, are very close to thermal noise limits and are quite symmetric. And so really the big asymmetry in the overall cell is caused by this difference in power in terms of the transmitter, and the uplink is significantly handicapped there. So you can see that as we get to cell edge and we're trying to transmit more power, we're only going to be able to extend a certain distance. And so to transmit wider bandwidths, we're going to have to naturally be closer to the tower in order to get the total amount of power per RB and the SNR improved. And you can see this arrow indicating high power UE. That's a special case where we're in the standard, we're allowed to transmit an extra 3 dB of power, and that has a big bearing on cell edge and overall coverage. So these aspects in terms of our data rates and our coverage get significantly improved as we move towards 5G. And what we're going to share next is sort of our expectations for how these smartphone features are really going to roll out, in what order and time frame, and what it'll actually mean in terms of what we can expect from these various stages in the development. So we start with stage 1, and here we're talking, as we mentioned, focus on downlink performance, more than a gigabit per second peak data rates, and improved latency. A lot of the overall characteristics tend to be focused where the network is really seeing most of the data traffic, which is the download of video. And stage 2, coming a little bit later this year and next, we're going to start to turn more attention towards the uplink, try to address a lot of the coverage issues and the data rates of the uplink using techniques and the transmitter from the handset. And in this final stage, much more disruptive technologies are introduced involving millimeter wave and beamforming. We'll talk a little bit more about that. And much wider bandwidths available at the very high frequencies, and huge significant increases, as Kevin mentioned, in terms of the overall capacity and data rates. So the first stage, getting to more closer to gigabit per second downlink performance. We've got carrier aggregation and aggregation of larger signals in bandwidth, up to 100 megahertz per channel now for 5G. We're introducing on the downlink much higher order modulations, 1024 QAM, which is basically 10 bits per symbol now, to get more bits through in a given second for the transmission. The MIMO order, 4x4, and that 4 times multiplier, very critical. And of course, we're supplementing that with a lot of additional technologies to even wider the spectrum even more. So license, assisted access, where we're using unlicensed bands for cellular communication, and we supplement in aggregation of extra channels in these unlicensed bands, and CBRS and other extended bandwidth, kind of opportunistic use of available free spectrum in order to add things in. And those are going to be very important as we try to get as much bandwidth use as we can. When we get to stage 2, typically, of course, the downlink is not going to stay static. It'll keep improving and expanding in capability. Uplink will become more important. There's going to be more uplink carrier aggregation for wider bandwidths overall. Modulation orders increase in terms of bits per symbol there as well. And in the premium tier, again, depends on the total architecture and implementation details, that you'll be able to support 2x2 uplink MIMO to double the uplink data rates. And again, extended use of unlicensed bands that will even involve transmit from the smartphone. So all of these aspects will continue to move to try to get the uplink improved significantly as well. And stage 3, we start to see a more advent of millimeter wave technologies. Now, these are, as Kevin mentioned, in the range of 28 to 39 gigahertz in the first rollouts. And the advantage of going up to much higher frequency is that we have a lot of spectrum available. So much wider channels and a lot of available spectrum. And so these the much higher frequencies enable a wide range of various advantages for the radio communication, one of which is that the antenna area or volume that's taken up by the antenna is a strong function of the overall frequency. And at much higher frequencies, the antennas will shrink and become quite small. And that enables us to basically, instead of a single patch or planar inverted F antenna structure, you can actually have a large number of these different antenna elements. And you can use those through phasing and coherence to be able to form and navigate point beams, which are much sharper in nature and more direct, and has a huge advantage in terms of the overall signal to noise that you're trying to send at these much higher frequencies, where path loss and obstruction can be a big challenge. You really want to be able to point all of the energy of your communication link in just the right direction. And another unique advantage of this whole technique of beamforming is that beyond just that you're only sending energy where you intend, is that you're not interfering with anyone else. So we've based all of our radio technologies for decades now based on trying to transmit omnidirectionally for robust reception, no matter where the user is in the cell. And similarly with the smartphone, to be able to connect with whichever tower is locally or closest or in a general area. But now we've reached, as Gabriel Rebez from UCSD likes to say, we've reached the end of the Marconi era, and this new beamforming approach will allow us to eliminate all of this wasted energy that causes interference with other users. It's a huge aspect that over time, the biggest impact that we have seen in terms of trying to improve data rates has been to decrease cell size and densify the cells. And beamforming does exactly that. You direct the beam and the entire resource, the entire bandwidth, these very large portions of spectrum, and you can direct it just to a single user. It doesn't have to be shared among many, many users. And so that's a huge efficiency that will allow a significant increase in data rates. We also, of course, have new waveforms as part of 5G, and we have that for sub-7 gigahertz as well. But in the new higher frequency spectrum, there's certain unique enabling aspects of the new waveform for 5G that we expect as well. And of course, this huge portion of new available spectrum that can be used. So some of the challenges are that this millimeter wave technology involves a lot of beamforming complexity. There's a lot of challenges to battery life that we'll talk about a little bit. There's also cost and area considerations in the smartphone. So mobility is really a big challenge for millimeter wave. Power amplifiers themselves will have some impairment in terms of a limited efficiency or ability to convert DC power to these very high frequencies at RF. The waveforms themselves have a very high peak to average, and that can also impact the overall amount of backed off power or headroom we have to allow and the efficiency. And there's matching losses at the higher frequencies. We tend to see more loss at the higher frequency. And all of these things tend to impact the overall battery consumption for mobile. So overall, when we look at all the opportunities with 5G new radio or NR, really this wideband capability is really an important aspect. And what I've shown here is sort of the sub-7 gigahertz range of spectrum. These bands on the left, low band and mid band and high band, as we typically refer to them, are over limited frequency ranges, and they extend the bandwidth to about a couple hundred megahertz total for a given pass band. But newer bands are being opened up, and this new spectrum is a big portion of why 5G in this frequency range is really going to have huge advantage for data rate. And this spectrum now produces bands which are much, much wider. And so there's a lot of challenge in terms of developing power amplifiers and low noise amplifiers and filters that can manage these large static passband bandwidths. In addition, we have the wider channels. And so as we get to 100 megahertz or combinations of 100 megahertz channels, the instantaneous modulation is a significant challenge to the active paths to be able to amplify with low memory effects and to be able to maintain integrity for error vector magnitude and the overall bit rates as we maintain linearity for these really wide channels. So the message here is just that the complication for just the bandwidth issues goes up significantly. As we mentioned, the real goal is to turn every single radio path on in the phone at the same time to be able to use them simultaneously. When we do that for 5G, there's a lot of multi-transmission modes which are required in the early rollouts. We have multiple uplink carriers in the handset at the same time, and we have a lot of intermodulation distortion to manage and other filtering aspects. So these complexities, not just in terms of the overall linearity and how to design and architect the front end, but also how to test these thousands of use cases where we have to combine these very complicated combinations of signals. It's really a huge challenge in the radio. So in order to address these, we typically architect similar to what we show here. We have 4 antennas in this case, as we show. 4x4 downlink MIMO requires, of course, the 4 antennas, and that's a mandatory feature support in many of the new 5G bands. But we show transmit-receive modules that have capability for both transmission and reception, and these LFEMs, or DRX kind of receive-only modules that are used just for reception paths, that these are combined across the antennas. We have antenna plexers that bring these different band groups and different frequency ranges together and merge them onto common antenna feeds. And of course, all of these modules need to operate in the presence of active operation for all the others. And so there's a lot of complexity overall. So, Kevin, that's a summary slide. I'll hand it back to you to wrap up.
Thanks, Dave. So I think hopefully we've exposed you a little bit to 5G. I think to us it's really exciting time. So anytime there's new disruptions, there's new technology, it's just a great time to be in the industry. Very exciting things happening. I think what really strikes me about 5G is we're just early on, and every day we're learning about new applications, new things that we hadn't thought before, and I think that's the one of the things that we have to be careful of is, do we always define things as a smartphone? Do we always define it as what we just last had? I think there's going to be many opportunities where we're going to have just different devices, different use cases, things that we're not even thinking about today are going to exist in 10 years and 5 years. So I think that part of it is very, very exciting. It's all being done to really make sure that, the data experience is complete mobility. It's fiber-like, Ethernet experience anywhere, anytime in the world. And that's just, that'll free up economies, that'll free up, things in the world that we don't know about. It's really just, it's going to be a driver for different industries, different economies, in different regions of the world. I think what you're seeing is we're going to have different solutions depending on what part of the spectrum that will be. But we've seen an industry that really comes to a challenge. If there's a challenge, we usually typically solve it. We solve it within a year or two. So we've been involved in the early days of development. So we're trying to figure out how do we make those solutions that are going to be ready for 2021, 22. We're already working on that now. But I think it's an exciting time. From an end user, a consumer experience, I think you're going to have dramatically revolutionized performance on devices. And again, you're going to have devices that you don't even know you want or need yet. So it really will be quite different. It's going to be a funny time, 2019, 2020, 21, 22. Even we started looking at this market a couple of years ago. We made some predictions. We looked at them a year later, and they were, we drastically changed a lot. We got closer to release 15. We made our assumptions on what the first devices were. We're constantly changing those. So I know in a year's time, I'm going to look back and say things are going to be different. But I think you're going to be living through a world that's going to have improved performance. The devices and the experiences are going to be more tailored and more customized to what each individual consumer wants. And I think that's the opportunity for the network providers and the device manufacturers, as well as RF front-end providers and chipsets. The opportunity is really segment those and make sure we're doing the right things for the right time at the right price point. And I think you're going to see exciting times that are going to be revolutionary over the next couple of years. So I just want to go to the next slide. We do have a landing page at Skyworks. It's our 5G website. So there's material there. There's white papers and some videos that you'll see there as well. And stay tuned. It's going to be exciting times. Lots to happen. A lot of activity, and we will be in the middle of it. So appreciate your time. So Kathy, I'll turn it over to you.
Thank you so much. This is awesome. We have about 5 minutes left. If anyone has any questions, and I see one just came in, which I'll share with y'all. How will I be able to tell if my smartphone supports 5G?
Oh, that'll be easy. You'll look down at the indicator and it'll say 5G.
Okay.
No, I tease a little bit, but that's actually what you will see, right? I think that the networks, say you are a T-Mobile customer or an AT&T customer, if you want to talk about the U.S., they will do a lot of branding for 5G. You're already seeing that almost daily between the four operators in the U.S. You go to the Korea, you're going to see the same thing. If you go in Barcelona, there's going to be a Mobile World Show. You're going to see nothing but 5G. So when they're ready to show you 5G, you will not be surprised. You will know it. There'll be plenty of advertising, plenty of messaging around 5G, and they'll probably get you on a new data plan too.
Absolutely. I see there's one more question that just came in from Tammy. What is the use model for mmWave and 5G, and will it be available everywhere?
So millimeter wave is very interesting. So, a couple of years ago, I would have said, there's no way we'll put millimeter wave in, but it's really being driven by the operators. They're serious about deploying it. The use cases are going to be quite different. It could be anywhere from a fixed wireless application, but I actually see more benefit in maybe a office, indoor office environment where you need to transfer a lot of data very quickly. So, and that may take a different device. It may not be a handset. It may be a different millimeter wave specific device that just quickly gets data. So really what we're trying to do in any 5G, whether it's millimeter wave or sub 6 gigahertz, it's really to improve the data experience. And on millimeter wave, I think there's a lot of use cases that aren't even fully fleshed out yet. But operators have the spectrum, and they'll figure a way out, and we're going to figure a way out to help them.
That's awesome. This has to be a really exciting time for you guys to be working in this industry.
Good times.
Yeah, absolutely. Absolutely. We've got 2 more minutes if anybody else has a question. And I know there was a couple earlier questions, and I believe Kevin answered them. They've been pretty much taken care of. Here we go. We have a comment here from Niels. mmWave can be used for wireless docking, VR glasses, and stuff like that.
I think so for most of the really high data rate point-to-point kind of communications, much like we use Wi-Fi today in certain hotspot locations, there'll be a lot of commonality there. There's also a lot of application in the backhaul as we try to build out these very high performance, high data rate networks that the fixed wireless from tower to tower might be able to more flexibly and better connect 5G services to all of us through the network.
That's awesome. Well, we got one more from Brian. Who is going to pay for all this data? At 1 gigabit, I can use my whole $100 a month data package in less than a minute.
Let's hope you download the right video. So the way that we most use our phones today, it's kind of interesting that we may download a video, and the operators actually want to kind of meter out. They want to fill your buffer and make sure that you've got 30 to 40 megabits per second so that your Netflix movie comes through okay. But then they quickly want to move on to other users and service them as well with this shared resource, and then come back to you quickly so that they can make sure your buffer maintains service and that you don't get interrupted or have a latency problem. But they don't really want to download the entire 5 gigabit movie to you. in a matter of seconds, because most of those data bits may not be watched. You watch the first few seconds of your cat video and then you move on. And so they really want to make sure that when they're sending bits across the valuable resource of the network, that they really get consumed entirely. And so that's really the kind of way that we're using our phone now at much lower data rates, and the constancy and the requirement for latency is really low. But it's very hard for us to see these peak data rates. One of the only times that you may see it is when you invoke the speed test on your phone to check what is the actual peak data rate. But it's always been the case that you build a bigger pipe and you think you'd never need that much data rate, and people will start to use it, and it starts to fuel demand, further demand. Applications arise, like Kevin mentioned, that we can't expect, and then suddenly it's not enough, and you need to do even better.
Yeah, absolutely. Well, David and Kevin, I want to thank you so much. This was such a valuable hour, and I want to remind everyone there was so much great information shared and great information on the slides. If you do want to come back and listen to the recording, I put the link at the top of the chat box, but it's witi.com/webinars with an S/archive, and that's where you'll actually find the recordings that we've done in the last couple years, so please do take advantage of that. So David and Kevin, thank you again so much. We so appreciate your being with us.
Thank you. Thank you very much.
Thanks. And thanks everybody for joining us, and we'll look forward to seeing you the next time. Take care, everybody. Bye-bye.
Bye now.
Bye.